Hi, this is Brad Strabing, and today we're going to talk about water hardness, or the hardness that's dissolved in water. Last we talked about dissolved ions in solution, those things that pass through a filter and remain after the water is evaporated. The things that remain, that are multivalent in nature, are responsible for what's called the hardness of water. And this is called hardness because it can create a hard scale that reduces the life of steam boilers and hot water heaters in homes and industry. The hardness is defined as the concentration of the multivalent cations measured, and this is a unit thing, a convention in engineering, that hardness is measured as if all the hardness is attributed to calcium carbonate. We'll come back to what that means in just a moment. But the cations that are in solution that are actually responsible for that hard scale mostly consist of calcium and magnesium in most areas, but may include some other multivalent cations such as ferrous iron, ferric iron, strontium, manganese, and other plus 2 compounds that are dissolved in water. There are two general parts of the hardness components. There's the carbonate hardness, which is less than or equal to the carbonate alkalinity or carbonate ion concentration in solution. These carbonates are easily precipitated in hot water because the solubility of calcium carbonate decreases with increasing temperature. This is a relatively unusual phenomenon, but true, and results in the formation of a calcium carbonate or limestone-like coating in hot water heaters and industrial scale boilers, which can reduce the efficiency and lifespan or design life of those boilers. The non-carbonate hardness is whatever is left after the carbonate hardness is exceeded. Water that is particularly hard requires increased soap for bathing and washing clothes and may form this hard scale in cooking vessels, piping, and other industrial processes. This table summarizes the types of hardness, where we have the total hardness, which is defined as the concentration of the diprotic ions, or multiprotic cations, and the units that it's expressed in are as milligrams per liter, as if all the hardness were measured as calcium carbonate. What does this mean? We may actually measure the mass of the scale that's collected, and the most prevalent compound in that mass will be calcium carbonate. So we just assume that the total mass is composed of calcium carbonate. There may be manganese in there, magnesium, some iron compounds as well, but we're going to make the assumption that they all have the same molecular weight as calcium carbonate. So when we calculate the hardness in water, we measure it as if it were all calcium carbonate. The actual carbonate hardness comes from the carbonate or bicarbonate ion concentration in water, and that may be equal to or less than the total hardness, whichever is less. The non-carbonate hardness, then, is the total hardness minus the carbonate hardness, similar to the solids concentrations that we were just doing. All these are measured in milligrams per liter as if they were calcium carbonate. The hardness of water can range from extremely soft, 0 to 50 milligrams per liter is calcium carbonate, very soft to moderately hard, 50 to 100 and 100 to 150 milligrams per liter respectively, hard water, 150 to 300 milligrams per liter, and then very hard water, greater than 300 milligrams per liter calcium carbonate. Even in the homes, most people would put in a hardness or water softening system or hardness removal system that you may have heard of, and we in fact had in one of our homes that I lived in the past. A water softening system that exchanged the calcium and other multivalent cations for more soluble monovalent cations in solution to soften the water and extend the life of the water heater and make clothes washing more efficient. Nationwide, we can see that there are areas of hard water where the water has been fossilized and dissolved in the minerals, particularly limestone-rich regions, for very long periods of time. This includes the Agala Aquifer that covers a good part of the Midwest. Other localized areas of hard water can be found wherever there are limestone deposits. The water hardness varies greatly from place to place, with some areas having very soft water, others areas having very hard water, depending upon the geology in those particular regions. So let's look at an example to determine the hardness. Water hardness was measured throughout various spring water wells in Pennsylvania many years ago. In this particular spring CU29 was measured in Cumberland County, Pennsylvania, and is described in Table 4.7. It has several cations that were measured in solution, sodium, calcium, and magnesium, and several anions, some nitrates, some sulfates, some chlorides, and some carbonates. Notice here that the carbonate concentration is 300 milligrams per liter, quite high already, and as we would expect, the calcium is the major positive multivalent cation, followed by magnesium, rather typical for dissolved species, particularly in this area, which is a limestone-based area, where we would expect relatively high levels of calcium. The first thing we'll do is calculate the amount of calcium in solution, as if all the calcium in solution were to form calcium carbonate. We start with 95 milligrams of calcium plus 2 per liter in solution, and we multiply by 1 over the molecular weight. Since we have milligrams, we'll use millimoles. So on the far left-hand side of this equation, we have the given amount of calcium in solution. We convert to the moles of calcium in solution, and we note that for every mole of calcium in solution, it will form 1 millimole of calcium carbonate. The molecular weight of calcium carbonate is 100 milligrams per millimole. When we multiply this all out, we're left with 237.5 milligrams per liter of calcium in the water. That's the weight that the calcium would form with if it reacted with and formed the solid with calcium carbonate or a limestone scale inside a pipe or water heater or a boiler. Similarly, we'll do the same calculation for magnesium. Now I do want to note in yellow, there may be an error typo in your book. From the previous table, we see that there were 13 milligrams of magnesium in solution. The molecular weight of magnesium is 24.4. Now because this has a charge of plus 2, 1 millimole of magnesium will also likely form a scale of magnesium carbonate. But in this case, we're going to assume that it's actually calcium carbonate that forms. This wouldn't actually happen, but we're going to group these all together as if it were calcium carbonate. So we're going to have 1 millimole of magnesium for every millimole of calcium carbonate that could potentially form by mass. Again, the weight of the calcium carbonate is 100 milligrams per millimole, and we're left with 53.3 milligrams per liter as if it were calcium carbonate. So that's the weight of the magnesium if it were to instead form a scale like the magnesium carbonate. The total hardness then is the sum of the diprotic ions, the calcium and the magnesium, or 237.5 plus 53.3, or for a total of 326.8. Therefore, from the table, we see that this groundwater is particularly hard. As mentioned, we are in a limestone region, so this is relatively common in some areas that are heavily limestone-based geology. The next thing we need to do is to calculate the amount of the bicarbonate in the water and how much calcium carbonate it could potentially form in solution. We were given that there was 300 milligrams of calcium of the bicarbonate ion, HCO3-, per liter of solution. The molecular weight of the bicarbonate ion is 61 milligrams per millimole. So we convert to the moles of the bicarbonate ion, and we note that there's 1 carbonate ion in each mole of calcium carbonate, so that we have a 1-to-1 ratio of the bicarbonate ion to the calcium carbonate ion. Again, we're converting this as if it were to form the calcium carbonate, so we multiply by the molecular weight of the calcium carbonate, 100 milligrams per millimole, giving us a total mass of 491 milligrams per liter if all the carbonate in solution were to form calcium carbonate. Now it's important to note in this case that the bicarbonate concentration, the HCO3-, is greater than that of the concentration of the dissolved ions. So therefore, the total hardness will be equal to the carbonate hardness. What this means is that there'll be excess bicarbonate ion in solution after it all reacts with all the calcium and magnesium in solution. Therefore, in this case, the carbonate hardness is equivalent to the total hardness, 326.8 milligrams per liter of calcium carbonate, and not equal to the concentration that could potentially form, because in this case, there's not enough dissolved calcium in solution to form that scale. Because there was so much bicarbonate in solution, and it would react with all the calcium carbonate in solution, there is no non-carbonate hardness in solution, since the carbonate hardness is greater than the total hardness. Here's another example to go through. Here we have a list of cations on the left-hand part of the table, and a list of anions on the negative ions on the right-hand part of the table. All concentrations given in milligrams per liter of the ion itself. We want to determine the total hardness, carbonate hardness, and non-carbonate hardness. Again, step 1 is to convert each of the divalent cations, because those are the only ones that will contribute to hardness, to their concentration in milligrams per liter as if they were to form calcium carbonate. We started with 12 milligrams per liter of calcium plus 2 in solution. When we multiply out by the molecular weights, we have a ratio of 20 milligrams per equivalent of calcium carbonate and 20 milligrams per equivalent of calcium. Notice here we used our equivalent units, and this is common when dealing with ions. There are 2 charges associated with calcium, so there are 2 charges associated with each mole. Since the molecular weight of calcium is 40 milligrams per mole, and there are 2 equivalents per mole, that means there are only 40 milligrams per equivalent. If calcium carbonate were to ionize in water, there would be 2 equivalents with each ion, meaning that this molecular weight, or the normality of the calcium carbonate in solution when converting to calcium carbonate, is equivalent to 50 milligrams per equivalent charge. We can do it the other way with molar weights as well, and we'll still end up with the same answer of 30 milligrams per liter of calcium in solution that would potentially form calcium carbonate as a scale in pipes for this example. We'll do similar calculations for magnesium, starting off with 15 milligrams per liter. Again, multiplying by the ratio of the molecular weight or equivalency of the calcium carbonate to that of the magnesium. This is a shorthand notation from what we did before, and will give us 60 milligrams per liter. We'll do a similar calculation for the other multivalent ion, the strontium in water, which was 3 milligrams per liter, and would form 3.4 equivalent weights of calcium carbonate. The total hardness then is the sum of all these compounds, equal to about 95 or 94.9 milligrams per liter as calcium carbonate. In this case, the majority of the hardness comes from the magnesium in solution. Next, we'll convert the carbonate to hardness. We had 75 milligrams per liter of the bicarbonate ion. We multiply by the ratio of the molecular weights. Notice in this case, since the bicarbonate ion, HCO3, only has a charge of -1, we have the same milligrams per equivalent as its molecular weight. In this case, yielding an equivalent production rate of calcium carbonate, 61.5 milligrams per liter. In this case, the carbonate hardness is less than the total hardness. When that happens, the carbonate hardness is equal to the calculated value that can be reduced from the amount of carbonate in solution, or 61.5 milligrams per liter of hardness. So the non-carbonate hardness can be found from simply rearranging the equation for total hardness, which consists of both parts, So the non-carbonate hardness in this case is our total hardness minus the carbonate hardness, 994.9 milligrams per liter of total hardness minus 61.5 milligrams per liter of carbonate hardness to yield a non-carbonate hardness of 33.4 milligrams per liter as calcium carbonate. Again, we can go to a graphical determination of this, where we see the total hardness is comprised of the hardness associated with the ions of calcium, magnesium, and strontium. There's a carbonate hardness of 61.5 milligrams per liter, and the remaining is made up of other anions and is part of the non-carbonate hardness. This will help us if you ever run into water softening issues with water that's hard in an area because of too much limestone and too much dissolved solids in the solution.